Hello everyone, welcome to my class. In my previous video, we discussed electromagnetic spectrum. So today we will talk about atomic spectrum. Atomic spectra or atomic spectrum. Simply the spectrum of the electromagnetic radiations emitted or absorbed by an electron during transitions between different energy level within an atom. Now, when an electron gets excited from one energy level to the another, it either emits or absorbs light of a specific wavelength. The collection of all these specific wavelengths of the atom in a given set of conditions like pressure, temperature, etc. is the atomic spectra of atoms. Electromagnetic spectrum consists of radiations of different wavelengths and frequencies. These can be separated and then analyzed with the help of an instrument called spectroscope. Spectroscope consists of a prism or diffraction grating for the dispersion of radiation and is also provided with a telescope to examine those radiations. If the telescope is replaced by a photographic film, then the same instrument is called spectrograph, and the pattern of the emitted radiation that is recorded on the film is known as spectrum. Now, spectrum is of two types. It can be continuous as well as line spectrum. Continuous spectrum and line spectrum. Continuous spectrum we have already discussed in our class 10. When white light is allowed to pass through a prism, then that white light splits up into 7 bands of colors, into 7 colors. These 7 colors, they are continuous, means they are mixed up. There is no separation line between these colors. So such a spectrum is called a continuous spectrum. Coming to the line spectrum, a spectrum in which only specific wavelengths are present. Those spectrums are called line spectrum. Line spectrum can have bright lines with dark spaces between them. Now, electromagnetic spectrum is a continuous spectrum because it consists of range of electromagnetic radiations arranged in the order of increasing wavelength or decreasing frequencies. It extends from radio waves to gamma rays. Now, we can further classify the spectrum into two types. One is the emission spectrum, another is the absorption spectrum. Depending upon the nature of the radiations emitted or absorbed, the spectra are of two types. Number 1 is the absorption spectra and number 2 is the emission spectra. Now, absorption spectrum is constituted by the frequencies of light transmitted with the dark bands when energy is absorbed by the electrons in the ground state to reach higher energy states. For example, let us talk about sodium chloride, the absorption spectrum of sodium chloride. So when light is allowed to fall or pass through the sodium chloride solution taken in a tube and the transmitted light is studied, now that transmitted light is allowed to pass through a prism and the spectrum is recorded, that spectrum will consist of otherwise a continuous spectrum having two dark lines. The two dark lines corresponds to the wavelength 5890 and 5896 angstrom respectively. Means these two lines have been absorbed by sodium chloride. That's why these two lines are not visible in otherwise continuous spectrum of sodium chloride. So this is the absorption spectrum of sodium chloride. Next is emission spectrum. When energy is absorbed by electrons of an atom, electrons move from lower energy level to the higher energy levels. However, these electrons, they have to emit energy to return to their ground state from the excited state which is unstable. Now, the frequencies of light emitted in such cases form the emission spectrum. The emission spectrum of the radiations can be produced by different ways. Number one, radiations can be emitted from the sun, means by radiations emitted from sun. Number two, by passing electric discharge through a gas at low pressure. Number three, by heating a substance to high temperature. Given below is a diagram of emission spectrum of sodium. When we heat sodium chloride on a platinum wire in the Bunsen burner's flame, and the emitted radiations are allowed to pass through a narrow slit, and then they are allowed to feed on the prism, and the spectrum is recorded on the photographic plate, then on the photographic plate we will observe only two yellow colored lines. These two yellow lines corresponds to 5890 and 5896 angstrom. It means that these two lines are emitted by the sodium chloride. So, when we discussed the absorption spectrum of sodium chloride, I told that these two lines were missing from the spectrum. But when we observe the emission spectrum of the same substance, only these two radiations will be emitted. So that means the continuous spectrum, the absorption and the emission spectrum, they are complementary to each other. The lines which we observed, which were missing in the absorption spectrum, they were only visible in the emission spectrum. So they are complementary to each other. Next is emission spectrum versus absorption spectrum. Means what is the difference between the two types of spectrum? The main difference between them is that an emission spectrum has different colored lines in the spectrum, whereas in an absorption spectrum there are some dark lines in the otherwise continuous spectrum. In detail, emission spectrum is produced when atoms release energy, but absorption spectrum is produced when atoms absorb energy. Number two, emission spectrum comprises of colored lines in the spectrum, but absorption spectrum comprises of dark lines in the spectrum. Number three, emission spectrum is helpful in figuring out the composition of a certain matter, but absorption spectrum can be used to figure out the ability of certain objects to retain heat and its absorption level. Number four, the type of photons emitted is helpful in figuring out the kind of elements and the substances made of, as such as each element radiates a different amount of energy and has a unique emission level. But the wavelength of light absorbed is helpful in figuring out the quantity of substances in the particular sample. Let us talk about the emission spectrum of hydrogen, or it is also called the line spectrum of hydrogen, line spectrum. Before we proceed, let us sum up that the emission spectrum is also called fingerprinting spectrum, because no two elements can have same emission spectrum. So that's why it is called fingerprinting spectrum, fingerprints. So let us discuss line spectrum of hydrogen in detail. Now, when an electron falls from one energy level in an atom to a lower energy level, it emits a photon of particular wavelength and energy. When many electrons emit the same wavelength of photons, it will result in a spike in the spectrum at this particular wavelength, resulting in the banding pattern seen in atomic emission spectra. The graphic to the right is a simplified picture of spectrograph. Now in this case, we have taken an electric discharge tube in which hydrogen gas has been taken, or you can say hydrogen lamp. The electric field is allowed to pass, which will be ionizing the hydrogen gas in the hydrogen lamp. Radiations were emitted. Those emitted radiations are allowed to pass through a narrow slit and then from the slit on the prism. Once they pass through the prism and the spectrum is observed on the photographic film, then we will be able to detect the 5 types of lines, 5 series of lines in the hydrogen spectrum. Those 5 series of lines are Lyman series, Balmer series, Paschen series, Brackett series and Piffin series. These 5 series of lines, actually Rydberg in 1890, he gave a simple theoretical equation for the calculations of wavelength of the spectral lines in these different series of hydrogen spectrum. So this equation is called Rydberg's equation or Rydberg's formula. That is 1 upon lambda or nu bar is equal to RH 1 upon n1 square minus 1 upon n2 square. Here n1 and n2 are integers. Remember, n2 is always greater than n1 for a particular series. n1 is ultimately an electron jumps to which state. So the ground state will be the n1 state, whereas the excited state will be the n2 state. So definitely for a particular series, n1 will be fixed and n2 should be greater than n1. Here RH is called Rydberg's constant, whose value is also fixed, that is 109677 centimeter inverse or 1.09677 10 raised to the power 7 meters inverse. So here in this table, I have defined the value of n1 and n2 for the various spectral series. Let us start with n1 equals to 1, means when an electron jumps back to the first level in an hydrogen atom, in the first level in an hydrogen atom from any shell, means from second, from third, from fourth or even from fifth and sixth level, but ultimately it is coming back to the first shell, then the lines corresponding to this will lie in the Lyman series. And Lyman series lies in the ultraviolet zone of the electromagnetic spectrum. When n1 is equal to 2, means when an electron jumps from any shell to the second shell, then all the lines corresponding to this particular series will fall or will lie in the Balmer series, which lies in the visible zone of electromagnetic spectrum. In case of Paschen series, the electron jumps from any shell to the third shell, means from fourth, from fifth, sixth, seventh, eighth, or from any shell to the third shell in a hydrogen atom. So when an electron jumps from any shell to the third shell, then the series of lines are called Paschen series, and the Paschen series, it lies in the infrared zone of electromagnetic spectrum. Similarly, when n1 is equal to 4, the values of n2 possible are 5, 6, 7, 8, 9 and so on. Means when an electron jumps from any shell to the fourth shell, from any higher shell to the fourth shell, then the line will lie in the Brackett series, and Brackett series also belong to IR zone of electromagnetic spectrum. Similarly, when an electron jumps from any higher shell to the fifth shell, the line will lie in the Piffin series, and it lies in the infrared zone of the electromagnetic spectrum. Though the formula was given by Rydberg in order to calculate the wavelengths or the wave number of all the lines falling in a particular spectral series, but in 1885, Balmer showed that if the spectral lines are expressed as wave number, then the visible lines of the hydrogen spectrum obey the formula 109677 1 upon 2 square minus 1 upon n square. Means here n1 is fixed for Balmer series. Value of n1 is equal to 2. So it is fixed. Now n can be 3, 4, 5, means it should be either equal or greater than 3. But n1 here is fixed, that is 2. For Balmer's formula, n1 is always equal to 2. So when we modify, when we substitute the value of n1 as 2, the same Rydberg's formula is called the Balmer's formula. Balmer's formula. And actually it was broadly applied on all the types of lines by Rydberg's. That's why the basic formula is Rydberg's formula. Rydberg's formula I explained 109677 1 upon n1 square minus 1 upon n2 square centimeter inverse, since it's a unit of wave number. So centimeter inverse. In this graph we have shown the hydrogen spectrum, hydrogen emission spectrum or line spectrum of hydrogen. Here one thing should be noticed, that is the gap between the two levels is decreasing. It is not same for all the shells. That is the distance between the first and the second is greater. Between second and third is decreased now. Between third and fourth will further decrease and so on. So the gap we need to maintain. Means the gap is not constant in the spectrum. So this point to be noted while drawing the line spectrum of hydrogen.